All right, this is your stat sensei, Mr. Spence, and this is a Zoom meeting going over for AP review. And specifically, we're going to be talking about units 1 and 2, or our units 1 and 2, which is collecting data, then displaying and describing data. Now, to be honest with you, most of this is going to be FRQ, but I'm going to start off with this first video is going to be primarily some multiple choice questions. And the reason I did that is because we're not going to, in the FRQs, we're not going to be going over bias. And a couple other things that I feel like I could touch very quickly with the multiple choice and be good review that way. So here we go. In a recent poll of 1,500 randomly selected voters, only 525 or 35% said that they did not vote in the last election. All right. However, a vote count showed that 80% of voters actually did not vote. So the claim was, they said 35%, but actual was 80%. Which of the following types of bias is most likely to have occurred in the poll? Well, we have non-response bias. Non-response is they didn't respond, so obviously that's not it. Sampling bias is not one. Selection bias is you just made it, the way you selected your sample was not good, so you're not going to end up with a representative sample. It's more of a overarching principle. Response bias is either the question is sensitive and people are inclined to lie, or they're tricked into giving an answer that is not accurate of their position. So that's response bias. And the last one is undercoverage bias. And that is the design of our study does not reach everyone in the poll. So the question is what actually happened here? So we kind of have to think a bit. They claim 35% of them said, yeah, I didn't vote. But in actuality, 80% did not vote. Well, we have to consider what's happening with voting. Even though it's not required by law to do so in the United States, it's kind of a civic duty, and there's a perception is that you should have voted. So they felt like they should have voted, so they guiltily said that they did vote even when they didn't. So this is response bias because, in fact, they intentionally misled. So misleading responses is going to be response bias or answers. Television news editor would like to know how local registered voters would respond to the question, are you in favor of the school bond measure that will be voted on in an upcoming election? By the way, please notice we're talking about a television news editor. A television survey is conducted during a break in the evening by listing 2 telephone numbers side by side on the screen, one for viewers to call if they approve of the bond measure and the others to call if they disapprove. This survey method could produce biased results for a number of reasons. Which of the one of the following is the most obvious reason? Well, we did not randomly select who was going to participating. The people chose to participate. And typically speaking, when we run a survey like that, those that choose to participate have very strong opinions one way or the other. So what happens is we have voluntary response bias, and even though this doesn't say it there, it gave me an opportunity to talk about it. This is a case of voluntary response bias where I was not randomly selected. I just volunteered my answer, and we will tend to overrepresent those who are in favor or substantially in favor or those who are greatly opposed. We will not get those in the middle. So people who feel strongly would have been my best answer for this one. Number 3, in a design of a survey, which of the following best explains how to minimize response bias? Well, basically, for minimizing response bias, we're trying to make the question less sensitive and phrase it in a way that's not leading someone to an answer. So since we're trying to do that, we're going to carefully word and field test our questions. We need to make sure very careful how it is phrased so that we don't lead someone to a false response, and so that we don't accuse them of anything. A scientist studying soil acidity, collected soil samples from a plot of land with a stream running through it. The soil samples came from land located on only one side of the stream. What is the potential source of bias that might be result from the sampling method? Well, here's the problem. We only represented one side of the stream. We really don't know what's happening on the other side. Maybe the other side is an open field and beautiful, or maybe one side's open field and beautiful and the other one has a chemical plant. So we could end up with totally different sides of the stream with very different soil samples. So in this case, wow, for whatever reason, I do not have the appropriate, I don't have, my answers aren't quite right, but this is a case of undercoverage bias. And it's undercoverage bias because I didn't represent both sides. I only represented one side. And remember, bias is systematic. Our system is designed in such a way that we're going to overrepresent one part of the population, thereby underrepresenting another part. So we're representing one side of the stream, but not the other part of the stream. So this is a case of undercoverage bias. And by the way, I think I have about 11 of these, just so you know. Approximately 52% of all recent births were boys. But we took a random sample of 100 births, and 49 were boys and 51 were girls. Well, so now instead of the population really is 49%, but we ended up getting, so this is our P, but then our P hat was only 49%. The most likely explanation for the difference between the observed results and the expected results in this case is what? Well, in this case, we took a simple random sample. So the very fact that we did that means we can't have bias. Please note, when we take samples, not all samples are going to look like the population. Your sample, my sample, and someone else's sample could be slightly different, and everyone took a nice random sample. Well, the result, that is due to sampling error or variability in the sample. This is due to sampling variability, also referred to as sampling error. Please note, that's a totally different thing than bias. Bias is the result of a badly designed study, whereas sampling error is the result of each sample, because it's not every person in the sample or everything in the population, we're going to have a certain amount of variability. So your sample, even though it's a random sample, may differ than my sample. And we expect that to happen. It's typical, and it can be explained by probability, and we can plan for that. All right. Question 6. A survey was administered to parents of high school students to a certain state to see if the parents thought the students' academic needs were being met. To select the sample, the parents were divided into 2 groups. All right. Point something out real quickly. If I divide it into groups, I'm dealing with one of 2 types of sampling. I'm either doing with a stratified or I'm doing with a cluster. So let's read on. One group of parents who live in the cities with populations of more than 100,000. So we have a common characteristic here. And the other group live in cities with less than 100,000. So we have 2 separate groups that are divided based on a particular characteristic. If you're divided on a characteristic, this is going to be stratified. Because remember, a cluster should have everything mixed together, and the cluster should look like the rear view mirror of the car. It sees everything, just a smaller version of it. Whereas a stratified sample is broken down on a characteristic. So in this case, when it asks what type, it's a stratified sample because we broke it down on a common characteristic. One other point to make here, stratification is for surveys. Stratification is for surveys or observational studies. Blocking is the same thing, but only applies to experiments. Number 7, the buyer for an electronics store wants to estimate the proportion of defective wireless game controllers in a shipment of 5,000. From the store, the shipment consists of 200 boxes with 25 controllers. The buyer numbers the boxes from 1 to 200 and randomly selects a group or 6 numbers in that range. She then opens the 6 boxes and examines all 25 controllers. So what type of sample is this? Well, I selected a group and then I surveyed all. So if I select a group and I survey all, again, the key thing is selecting a group, because selecting a group means it could be cluster or could be stratified, but selecting a group and surveying all will be a cluster. Selecting a group and conducting a census will always be a cluster. At a large conference of teachers from a variety of subjects, a random sample of 50 mathematics teachers attending the conference was selected. So first off, we happen to be at a conference. We selected 50 math teachers. Now we have a variety of subjects at the conference, but we only selected math teachers. Among the selected mathematics teachers, 28% had taken 1 or more courses in statistics. For which of the following populations is 28% a reasonable estimate of the percentage of those who have taken 1 or more courses? All right, so all teachers who attended the conference, no, that can't be right, because we only looked at the mathematics instructors. We did not look at the one with all subjects. All right, we also can't be all teachers, because if you go to the conference, you may differ from teachers who don't go to the conference. For instance, I avoid going to conferences. So in my nature, I would not be represented, because I'm one of the people who avoid those if I can. All mathematics teachers, that ties to the all teachers. All mathematics teachers are not the same. I'm a mathematics teacher and I choose not to attend conferences when I can avoid them. So I'm not likely to be there. My group is not likely to be represented. So the next question, all mathematics teachers who attended the conference. That sounds pretty good, because we're generalizing to the group that we surveyed, mathematics teachers at the conference. And finally, the last one is all mathematics teachers who have attended who have taken 1 or more courses in statistics. This, even if it said at the conference, this was wrong, because we didn't survey just the ones who took statistics. We just took a random sample of math teachers at the conference. So because it's a random sample of math teachers at the conference, we can generalize to the population that looks like that, which are math teachers at the conference. All right? Because remember, we generalize to the population that our sample measures. All right? The sample has to look like the population. Moving on. A recent study examined 699 car accidents in Toronto over a 14-month period. Records of phone service providers were used to determine whether the driver was using a cell phone during or immediately before the accident. Overall, the researchers found that driving using cell phones were 4.3 times as likely to have an accident. The result was statistically significant. So what that's saying is that they ran a hypothesis test and found that the proportion of people having accidents who were on a cell phone was much greater than those who were not. So we ended up with a small p-value, so we rejected the null. That means it's statistically significant. So then I say, what can be concluded? The first question, cell phone usage increases the likelihood of a car accident. Likelihood is another word for probability, and we probably shouldn't make this claim. Although this is possible, probably shouldn't make this claim, because this was clearly an observational study. I didn't make them talk on the phone or not talk on the phone. So this was an observational study and not an experiment, and only experiments can show causation. I put a question mark by it because I can't completely eliminate it, but I hope there's a better answer. There is an association, there's a relationship between cell phone uses and accidents. Yes, statistically significant, but not necessarily a causal relationship. Oh, I like that very much. I'm going to get rid of A. And that's my answer. Because correlation or association does not prove causation. That can only happen if we conduct an experiment. This was an observational study, so we can't prove causation. Number 10, the manager of a public swimming pool wants to compare the effectiveness of two laundry detergents, detergent A and detergent B, in cleaning the towels that are used daily. As each dirty towel is turned in, it's placed into one of the washing machines on the premises. When the washing machine contains 20 towels, the manager flips a coin to determine which detergent. So will be used for that load. The cleanliness of the load of towels is rated on a scale from 1 to 10 by a person who does not know which detergent was used. The manager continues this experiment for many days. Which of the following best describes this study? So let's take a look at this. We put dirty clothes in a washing machine, or dirty towels in a washing machine. We flip a coin. We have two detergents. I'm going to call them D1 and D2. We flip a coin and place them in the washing machine. And then after we run the washer, we compare the results. We compare cleanliness. Well, in this case, I only have one assignment. I have no blocking. So this is a completely randomized design. And I did the random assignment by flipping a coin. Right? We flipped a coin in order to do the randomized design. So in this case, we have a completely randomized design, and our answer choice is A. Last of the multiple choice questions before we roll into free response. This is the very last one. A new restaurant is interested in determining the best time temperature combination for roasting a 5-pound cut of lamb. The times to be tested are 45 minutes, 60 minutes, and 90 minutes at temperatures of 350 degrees Fahrenheit and 425 degrees Fahrenheit for each time, with the exception of 90 minutes and the 425 degree combination. That combination is eliminated because it will overcook the lamb, which leaves 5 other combinations. From 10 identical cuts of lamb, 2 are randomly selected to roast using each of the time temperature combinations in the same oven. The quality of the finished product is evaluated for each roast. Which of the following is true? So in this particular case, I feel like it really helps to draw out a diagram of what we did. So basically, I randomly assigned, and I had 3 different time frames. 45 minutes, 60 minutes, and 90 minutes. So those are the 3 time frames. And then from there, I randomly assigned them to 350 and 425. And I randomly assigned again to 350 and 425. And I randomly assigned again to 350 and 425. Only we got rid of this one because we said it'd take too long. Well, I had 10 pieces of meat, and I have 1, 2, 3, 4, 5 treatments. Gosh, 10 divided by 5 is 2. That means this one got 2 cuts of meat. This got 2 cuts of meat. This got 2 cuts of meat. 2 and 2. So each one got 2 cuts of meat. And because I put it on more than one, I have replication. Please remember, replication is different in statistics than it is in science class. Science class says if I do the experiment over and over again, I expect to get the same results because everything is closely held in a laboratory environment. The data we're collecting isn't nearly as perfect. Just like when you follow the recipe, you can follow the recipe exactly and it'll differ from day to day. It just doesn't always turn out exactly the same. So replication in statistics means that we tried it on more than one thing. And so we tried this treatment on we tried each one of the treatments on 2 different pieces of meat so that we could generalize to the population of all meat of that type. All right. So we did replication so that we could generalize to all meat of that type. So the 2 cuts are being roasted for each time temperature are an example of replication, and that is E. I'm going to pause this for just a moment.